So, hello everyone. Today we are starting week 8, that is gas liquid mass transfer in bioprocess. So, as the name suggests, gas liquid. So, this week will mostly deal with two processes, that will be aeration followed by we will be discussing with agitation or mixing. But before we go ahead, first we will be discussing this mass transfer theories, followed by that we will go with this gas liquid system in bioprocess. So, we can quickly discuss what was there in the last module. So, in the last module mostly it included the operation of bioreactors, what are different components of bioreactors and how they are operated. So, if you remember this, it can be operated in a batch, fed batch and further in the continuous. Now, in the continuous mode, there is a both inlet and outlet, it operates at steady state. Batch, there is no inlet, there is no outlet. In the fed batch, there is only inlet and no outlet. But later on we have made some assumption, it is called quasi steady state. Because there is no significant change in the substrate concentration and biomass with time. Now, in the continuous operation, it can operate in two modes. First is if the flow rate is constant, it means F is constant F, that is called chemostat. So, this is basically done to have a certain concentration of limiting substrate in the feed. Other mode of operation is torpedo state. In the torpedo state, we maintain a constant cell density or turbidity, and for maintaining that the flow rate keep on varying, but thus at the same time inlet and outlet flow rate remains the same. So, here F is not constant, F keep on changing, but both inlet and outlet flow rate remains same. In the chemostat, flow rate remains constant. And in addition to this chemostat, we further discuss another mode of continuous operation, that is the PFR, plug flow bioreactor. Here the reaction progresses along with the length of bioreactor. Then further we discuss special bioreactors. There were different variations like bubble column, airlift, packed bed, fluidized bed, and at the end we discuss what should be the reactor consideration for shear sensitive animal cell and plant cell culture. So, today as I told, we will be discussing on mass transfer theories, and in the subsequent lectures we will be going ahead with aeration, then followed by agitation. So, mass transfer we will be concentrating on these two theory, molecular diffusion as well as two film theory. In the bioprocess, there are transport of nutrients, gases and product. It may be through the stagnant regions, it may be through the well mix region. And even if you see the well mix system, the last step is governed by the pure diffusion. And how this mass transfer occurs? There should be a driving force, and driving force is delta C, the concentration difference. And what is the typical flow behavior? It goes from the C1 to C2. It says C1 is greater than C2. What is the utility of mass transfer? As it is dealing with the transport of nutrients, gases and product. So, particularly in aerobic fermentation is important for oxygen supply. So, oxygen is supplied from the air bubble to the liquid medium. It is important for the solvent extraction. It helps to separate and purify your product. There is again mass transfer operation. Extraction is a mass transfer operation. For example, in case of penicillin extraction, the aqueous phase and organic phase is used for the extraction of penicillin, and we typically use butyl acetate as organic solvent. So, as I told, this reaction rate and how the substrate conversion, product formation or biomass growth is taking place, it depends on the mass transfer rate. Particularly, it is important in the gas liquid and liquid solid system. So, gas liquid mostly will be dealing in the aerobic culture, aeration, and liquid solid system will be dealing with this immobilized systems. It may be immobilized cell or immobilized enzymes. Now, gas liquid interface are the focus for oxygen transfer studies. We will be discussing during the oxygen transfer process. There are multiple steps, but the key step is this gas liquid interface, and particularly in the aerobic culture, if there is a limitation of oxygen, it directly affects the whole metabolism. Now, next is liquid solid mass transfer. This is important in pellets, flocks, clumps and films of either cell or enzymes. Now, typically if there is a slow diffusion, then this starving the cell in the pellet, this becomes oxygen limited fermentation, and at the end it leads to the poor product formation and product recovery. In addition, there is a nutrient limitation as well, because the solubility of certain nutrients in a given media keeps the solubility of nutrients in the given media are different. So, nutrient limitation can occur if liquid solid mass transfer is slow, because the rate of utilization of nutrient should be equal to the rate of supply of the nutrients. So, here if we just see if it is solid or solid fluid, the mass transfer mostly occurs through molecular diffusion. In the moving fluid, it is through the convective transfer, and in the bioprocess it involves both. So, in the bioprocess we see there will be both diffusion as well as the convective mass transfer, through which mass transfer of nutrients, gases and products takes place. So, first is the diffusion theory. So, before going to diffusion theory, we will be discussing this molecular diffusion. What is molecular diffusion? As the word suggests, it is a random motion of molecules from a region of high concentration to the low concentration, and that is driven purely by the concentration gradient, that is a driving force. So, molecules move from high to low concentration to eliminate this concentration gradient, and diffusion process continues as long as there is a concentration gradient. How do we achieve the continuous diffusion? By supply of material to high concentration region. Other option is removing of material from the low concentration region. So, these are the two approaches. It is very important that this molecular diffusion occurs even in these quiescent fluids and solids, and typically final step is in mixing where small eddies and stagnant zones are formed. We just see this diffusion is taking place at the very crucial steps in bioprocess operations. Now, if we just see what is diffusion, this is going from a concentration Ca1 is higher than Ca2, so it is diffusing. So, this becomes the direction of mass transfer, and this A is the area through which this mass transfer is taking place. Now, we will be discussing the Fick's law of diffusion, which describes the molecular diffusion in single and binary phase. So, it says Ja is directly proportional to concentration gradient. A is proportional to dCA upon dy, and the proportionality constant is diffusivity. dAb is the diffusivity, dCA upon dy. The J is the mass flux, let us say gram per mole per unit area per unit time. So, mole per meter square into second. Na is mass transfer rate, gram mole per second. Ca is concentration, mole per meter cube, and dA is diffusivity, its unit is meter square per second. This negative sign shows the mass flow opposite to the concentration gradient. Now, how can you increase Ja by raising the dAb by steeping this concentration gradient or enlarging the area, because the mass transfer is taking place through certain area. Here I have listed the typical diffusivity value of oxygen. Let us say oxygen diffusivity in the air is in the range of 10 to the power minus 5 meter square per second, but same in the water is 10 to the power minus 9. So, what it says, because it is very poorly soluble in the water. In the water, the solubility of oxygen is about 8 ppm. It is very less, because if you see the solubility of particularly other nutrients, it is in the gram per liter, and this is coming in the milligram per liter. Now, if you see this how diffusivity varies, it varies depending on the what are the component of mixture, basically both solute and solvent. So, it may be soluble in one phase, it may not be soluble in the other phase, and if you increase the temperature, we increase the diffusivity, because this increased temperature then molecular moment increases, and in the case of gas, if you increase the pressure, dAb varies with the pressure, and in the liquid diffusivity vary with the concentration. So, here what we have discussed so far, if you want to increase the diffusion rate, there should be higher concentration gradient dCA upon dy, larger area and higher value of diffusivity, and diffusivity depends on the both the component of mixture, its temperature, pressure for gases and concentration for the liquid. Now, before we go ahead, we will quickly see analogy between mass, heat and momentum transfer. In all three cases, the flux is proportional to driving force, and there is a proportionality constant, that is coefficient. So, in case of mass flux, the proportionality constant is the diffusivity, and we discussed this is a Fick's law. In case of heat transfer, the heat transfer rate is proportional to the temperature gradient. This is temperature gradient, and K is proportionality constant, that is thermal conductivity. And if you see the momentum flux, it is proportional to the velocity gradient. So, this shear stress, this is a shear stress, is proportional to the velocity gradient, and proportionality constant is viscosity, right. So, if just see in all three processes, this heat, mass and momentum transfer, the rate or the flux is directly proportional to the driving force gradient. In mass transfer it is a concentration gradient, heat transfer it is a temperature gradient, and momentum transfer it is a velocity gradient. Now, next we will be discussing what is the role of diffusion in bioprocessing. It is very important in the bulk mixing, and the first one is the mixing scale limitation. Let us say if you say this turbulent causes mixing only down to a small eddy size. Now, in the eddy size, within a small eddies the flow is almost streamlined and final mixing occurs through molecular diffusion only. In the solid phase reactions, reaction in solid phase, particularly this immobilized cell and flux, they require substrate to diffuse into the solid. At the same time product should also diffuse. So, let us say this is an enzyme, the substrate should diffuse here, and once the product is formed it should diffuse out, and there is no convection inside the particle, there is only diffusion handles the mass transfer. In general we have discussed it is called intraparticle diffusion, and if there is a slow diffusion it can limit the reaction rate significantly. And mass transfer across the phase boundary, phase can be a solid liquid, it can be liquid liquid, it can be liquid gas. So, particularly this oxygen transfer in the gas liquid interface, solvent extraction in the liquid liquid interface, and substrate intake in the solid liquid interface. So, near the interface the diffusion dominates the mass transfer operation. Now, after this molecular diffusion, next theory we will be discussing is film theory. So, whenever there are two phase meets, there is a formation of thin stagnant diffusion film, or we sometimes say boundary layer on each side of the interface, and when this diffusion film or boundary layer are formed, there we apply the two film theory. What are the key concept here? The bulk phase are well mixed outside the film, and mass transfer resistance almost entirely resides in this film. If I am having solid, so this is a film this side, and there can be a film either side as well. If I say this is gas phase and this is a liquid phase, and the interface is assumed at a local equilibrium. So, whatever the interface is there, we assume it is at equilibrium. So, let us see quickly two film theory. So, there is organic phase and there is aqueous phase. So, concentration is higher in the phase 1, this is lower in the phase 2. So, this is the direction of mass transfer. So, what will happen from bulk of the phase 1 to the interface, this is the step 1, or you can say mass transfer taking place in the phase 1 is coming at the interface, and then from interface it will go to the bulk phase 2. This is the phase 2, and each phase has a thin film. You just see both the sides, that boundary layer is present here. Now, if you just say if the concentration here is Ca1 and concentration here is the Ca2, so at the interface the concentration will be called Ca1i and this will be called Ca2i. And here if you notice there is some discontinuity here, and this discontinuity is coming because of the distribution or partition coefficient. Distribution or partition coefficient. So, what we are assuming, there is no mass transfer limitation in the bulk phase, it is limitation in the film, and at the interface we are assuming the equilibrium, and interfacial concentration differ due to partitioning or distribution coefficient, and even in the turbulent system we have discussed diffusion near interface is critical due to low fluid velocity. Now, how to write the equation when there is a convective mass transfer or there is a two film theory. So, we say the convective mass transfer occurs with the bulk fluid system, enhancing the transport rate beyond just molecular diffusion. This concentration gradients drives diffusion, but the fluid movements at the overall rate of mass transfer here, and especially when we are having this multi-phase system and where boundary layer offers resistance to the mass transfer, or you can say in the case of film theory we consider this convective mass transfer. So, in this case the rate of mass transfer is directly proportional to the area transfer area available for transfer as well as driving force, and the proportionality constant here is mass transfer coefficient. So, convective mass transfer, in this case the rate of mass transfer from bulk fluid through the boundary layer to the interface. So, where the mass transfer is taking place from the bulk fluid to the interface through the boundary layer. So, we are having this bulk liquid and this is your interface. So, from here it is going to here through the interface. The same can be written in this way. Na is a flux or mass transfer rate, K is a mass transfer coefficient, A is the interfacial area per unit volume, and CAB, B means concentration in the bulk, I means concentration at the interface. So, we write Na as K A Ca in the bulk and Ca at the interface. So, driving force is concentration difference, K is the mass transfer coefficient. How we can increase the rate here, similar what we discussed in the case of molecular diffusion, there should be higher concentration gradient, there should be large interfacial area and higher value of mass transfer coefficient, K, A and delta C. The same expression can be rearranged in this way, that this Na is K A delta C. So, Na can be written as delta C divided by K into A, or we say driving force upon resistance. So, the resistance is mass transfer resistance is defined here as K into A. And this film theory is very important, particularly in the gas liquid mass transfer, liquid mass transfer and gas liquid mass transfer. So, liquid solid mass transfer, liquid mass transfer and gas liquid mass transfer. So, particularly whenever there is a phase change. So, we will quickly see one case here, liquid mass transfer. So, you consider there is a aqueous phase what we discussed earlier. Let us say aqueous phase, there is a organic phase, and in one side the concentration is higher, let us say it is going from here, the concentration is Ca1, here its concentration is Ca2. So, first it will reach from here to here, this is a Ca1i, and from here it will go from Ca2i to Ca2. So, in the phase 1, what is the rate of mass transfer? We can write Na 1 as liquid phase, the mass transfer coefficient is KL1 interfacial area A Ca1 minus Ca1 I interface. Similarly, for the phase 2 or for the other side, this will be Na2 equals Kl2A. Now it is Ca at the interface, it is higher, so it will be Ca2I minus Ca2. Now, what is partition coefficient? Is the ratio of concentration at the interface. So, we define M equals Ca1I divided by Ca2I, and for time being let us assume the transfer rate of transfer from both sides is at equilibrium at a steady state. So, we say Na equals Na1 plus Na2. Now, in the equation 1 here what we can do, we can convert this Ca1I will be Ca1I equals M into Ca2I, and here what we can do, this Ca2I we can convert in form of Ca1I. So, this will be Ca1I upon M. So, you just see this is the same, equation 1 become equation 3 and equation 2 becomes equation 4. Now, what we can do, we can combine either equation 2 and 3. So, it will cover from Ca1 to Ca2, or we can combine the equation 1 and 4, it will combine from Ca1 to Ca2. So, first let us combine equation 2 and 3. So, what we are going to do, in the equation 2 you have to multiply with M. If you just see the equation 2 here, because this is divided by M is there. So, if you multiply here with the M, then you add with equation number 3. So, this becomes Na 1 upon Kla1 plus you multiplied with M Kla2A equals, so Ca1I minus M into Ca2. So, actually what is happening here, the interfacial concentration will be cancelled out. I will do here one, let us say I multiply equation 2 with M. So, this will be equation 2 with M and then equation 3. So, this becomes, let us say equation 2 multiply with M. So, this becomes M into Na2 divided by Kl2A equals, we are multiplying with M. So, this becomes M into Ca2I minus M into Ca2, and what is equation 3 is Na divided by Kl1A equals Ca1 minus M into Ca2I, and if you add these two, so basically this interface concentration will be cancelled out. This, if you add this will be cancelled out. So, we will be having Na will be taken out. So, this will be Na equals 1 upon Kla1 plus M upon Kl2A equals Ca1 minus M into Ca2, and this whole term is called now overall mass transfer coefficient. So, we write the capital K, 1 upon capital K L1A equals 1 upon small k L1A plus M upon k small k L2A. So, in this way we define this overall mass transfer coefficient equals Ca1 minus M into Ca2. Now, the same exercise we can do, equation 1 divided by M, we go to equation 1, this divide by M, then you add with the equation number 4. So, if you divide by N, so it becomes 1 upon M into Kla1 plus 1 upon KLa2, and here the overall mass transfer coefficient will be KLa2A equals 1 upon KLa2A plus 1 upon m into KLa1A, that equals, now here it was Ca1 minus m into Ca2, it will be Ca1 divided by m minus Ca2. So, in this way we get this mass transfer in terms of overall mass transfer coefficient. Now, we can do the same exercise for the gas liquid mass transfer. So, you just see this is a gas phase and this is a liquid phase, the concentration CAG in the gas phase, at interface it is CAGI, in the liquid phase at the interface concentration is CALI, and in the bulk phase it is CAL. So, for the gas phase the NAG is KGA, gas phase mass transfer coefficient, into interfacial area into concentration difference CAG minus CAGI. In the liquid phase mass transfer coefficient A into CALI minus CAL. These are the two equations, and as we discussed earlier you have to do the same exercise, then we will be getting this overall mass transfer coefficient for the gas phase as well as for the liquid phase. So, if you consider this phase, the final equation will be Na is KGA CAG minus m into CAL, and for the liquid phase the equation will be Na as capital KLA CAG upon m minus CL. The similar expression what we discussed in the case of liquid mass transfer. So, typically this value as it is in equilibrium, so many times we write this CAG minus CAG star. Similarly, this value will be writing CAL star, that is it. So, this is the terminology. At the equilibrium concentration we write in terms of CAL star in case of liquid and CAG star in the case of gas phase concentration. Now, one more important thing is here, this many times the value of, if you just see the expression of KLA 1 upon capital KLA equals 1 upon m into small k gas phase mass transfer coefficient plus 1 upon. So, as we have seen the solubility in the gas phase, as you can say the mass transfer in the gas phase is much higher. So, if this value is higher, so we can neglect this term. So, many times we find out that small KLA equals the overall mass transfer coefficient in the liquid phase. So, in this expression many times if overall mass transfer coefficient is not there, we directly go with this individual mass transfer coefficient KLA. Now, there are one couple of examples here based on the concept what we have discussed. So, for a gas liquid system KLA is 0.025 second inverse, CAG concentration in the gas phase is 6 mole per meter cube, value of m partitioning coefficient is 3. Say calculate the value of mass transfer rate if CAL is the liquid phase concentration is 1 mole per. So, this is very straightforward, the Na is KL into A, this is value is already given KLA to CAG upon m minus CAL. So, this is what we need to remember here, because Na is KLA CAG upon m into CAL, and if you put this value we will straightforward get the answer 0.025 mole per meter cube into second. In the similar way, it says in an aerobic bioreactor, we are cultivating E. coli and efficient oxygen transfer is crucial to support the optimal cell growth and metabolism. And these are the data which we got from the experiment is gas phase mass transfer coefficient was 0.01, liquid phase mass transfer coefficient was 0.02 second inverse, distribution coefficient was 2, estimate the overall gas phase mass transfer coefficient KGA. So, what is KGA? 1 upon KGA is 1 upon small kGa, this value is 0.01 is given here, divided by m upon KLa, m is 2, KLa is 0.2. If you put directly, we will get the KGA as 0.005 second inverse. So, I will stop here. So, today we discussed the mass transfer theory, particularly this Fick's law as well as two film theory or convective mass transfer. So, Fick's law, the driving force is concentration gradient, and for convective mass transfer the driving force is the difference in the concentration. Thank you so much.